Hi, this is Dr. Justin Esarey, and today we're going to talk about Bayesian networks, sometimes abbreviated as Bayes nets. A Bayes net, or a Bayesian network, is a way of recovering information about the structure of statistical dependencies among variables. So, what is a Bayes net? A way of recovering information about the structure of statistical dependencies among variables. Now, let's consider a very simple example of what I'm talking about. So I'm going to create a little 3-variable diagram here. 3 variables are A, B, and C. And I'm going to connect them with little arrows here. These are called edges. So these edges, which I'm going to sort of note here, an edge corresponds to a causal relationship or pathway. And a node, like B here, the little circle, is a variable. So what this diagram that I've just drawn here says is that A causes B and B causes C. And you can see that from the pattern of relationships. The node A has a directed edge, I should say, pointing toward B. That means A causes B. B has a directed edge pointing toward C. That means B causes C. Now, as I noted, a Bayes net is a way of recovering information about the structure of statistical dependencies among variables. But all of a sudden, I've started lapsing into this use of causality, right? And so causality as a concept is actually surprisingly difficult to define, at least in a way that would be considered philosophically rigorous. For our purposes of this discussion, I'm just going to define causality to mean the following. If A causes B, then changes in A will create consistent changes in B, holding all other factors constant. So that's our quick and dirty definition of causality for the time being. And like I said, Bayes nets recover information about the structure of statistical dependencies. And that may tell us something about the nature of causal relationships in a data set, or it may not. The trick is that causal relationships like the ones we've just depicted or create certain patterns of statistical dependency. So what do I mean here? Well, go back and consider the diagram that we just created. That's this one right here. This network of causal relationships is going to map very nicely onto a set of statistical dependencies. For example, the fact that A causes B implies that the distribution of f of A and B equals the conditional distribution of B given A times the distribution of A. The idea here being that because B is caused by A takes some realization that's in this case purely random, and then the random realization of A influences the distribution of the partially random distribution of B. So B is a random variable that's partially determined by A. Likewise, the relationship B causes C implies that f of B and C equals f of C given B times f of B for the exact same reasons. So the overall network of dependencies here tells us that f of A, B, and C will be equal to f of A times, I'm sorry, I wrote that down wrong, f of C given B times f of B given A times f of A. Just like that. So that network of dependencies is quite different from the network or from the pattern of dependencies that would arise from a different network. So for example, to consider this alternative network. A causes B and C also causes B. That network would imply a pattern of distribution that f of A and f of C were purely random, and then the realization of B would be contingent on A and C. So if we look at these two patterns of relationships, we can see that they're different, and we might be able to infer something about the networks that they came from. So in other words, what Bayes networks do is, or Bayes nets do, is look at the pattern of dependencies that we can observe in data and then try to come to some conclusion about which causal structure they came out of. So Bayes nets examine a pattern of statistical dependencies in a data set and attempt to come to some conclusion about the structural network of causal relationships that produced those dependencies. Of course, there are many potential pitfalls of trying to do this. In other words, this is not a magic bullet to recover causality. And one of the many problems with this, or one of the many limitations, I should say, with this approach is that there are different networks that produce similar patterns of statistical dependency. So, for example, consider the following network. A is caused by B, which is caused by C. Using the principles that we illustrated earlier, we would say that f of A, B, and C is f of A given B, f of B given C, f of C. Right. Which at first blush looks different from this pattern of dependencies that generates, or that comes from rather, this network where A causes B and B causes C. So in other words, you might say, well, the pathway going from C to A looks different than the pattern of, or the pathway going from A to C. But that's not so, which we can determine pretty quickly by using Bayes' rule. So if we use Bayes' rule to rewrite this pattern of dependencies a little bit, just to note, Bayes' rule says that f of A given B is equal to f of B given A, f of A divided by f of b. So I can use that to substitute in for this expression, and then I can use a similar substitution for this expression, and I'll get the following. F of b given a, f of a divided by f of b, times, now we're going to substitute for this expression here, f of c given b, f of c divided by f of, I'm sorry, I messed that up. Yeah, f of b divided by f of c. Oops. And then finally we've got this f of c out here. I can systematically cancel here and here. And what I'm left with is f of b given a times f of a times f of c given b, which you'll note is exactly identical to the pattern we developed right here that corresponds to this network. So the point of this is that not all graphs, let me say this a little bit different way. All graphs imply a unique pattern of statistical dependencies. But not all patterns of statistical dependency uniquely imply a graph. And that is a problem because when we look at a data set, we don't get to look at a graph, we get to look at a data set. And so and when I get my data set, I won't necessarily be able to say that this data set implies one and only one network of causal relationships. That's one problem, and that's a pretty significant one in the sense that there is going to be some degree of ambiguity, at least in some cases, that comes out of our analysis. It's definitely not the only problem. For example, if we omit variables from our analysis, we could well run into a problem. If there's endogeneity in a data set, which is to say that A causes B and B causes A, you'll see in a second that Bayes nets are also going to face problems. But this is a pretty notable issue because even when everything's working appropriately, it puts a limit on what we can infer from observed data. Now the good thing is that we can distinguish a lot of things from each other on the basis of conditional dependency. So for example, as we saw earlier, this graph where A and C point to B or cause B, which implies that relationship of dependencies, that can't be mistaken for something like this. So the pattern of dependencies that comes out of this graph, which we just saw, can't be mistaken for the pattern of relationships that come out of this graph. So based on the pattern of dependencies we observe, we're going to be able to rule out many potential causal networks that we could think of, which is good. The only issue is we might be left with more than one candidate causal network after we're done with our analysis, which is not so good in the sense that it leaves ambiguity in what's really happening. So one just added note here, what sort of things can we tell apart and what sort of things can't we tell apart? Well, we've already noted a couple of things that kind of fit into this distinguishability category, or which things are distinguishable and what things aren't distinguishable. So we've already noted that we can distinguish something like this from something like this. But we can't distinguish something like this. So in other words, these two things I can tell apart, but I can't tell this thing over here apart from this. The reason for that is pretty straightforward. It's just a general application of the idea that Bayesian networks can't really tell the difference between something like this and something like this. This is sort of an instantiation of the idea that correlation is not the same thing as causation. This pattern of causal relationships implies that we should model things as this. Whoops. Should be B. This sort of causal relationship argues that we should say that A is independently distributed and then look at the conditional distribution of B given A. Should be A given B, sorry. But Bayes' rule says that these two things are the same because I can convert f of A given B to f of B given A, f of A divided by f of B, cancel out, and I get the same thing. So you're just sort of seeing an example of the principle that if A and B are related statistically, I don't know which causes which just from that bit of information alone. So I can't tell the difference between these two things, which means I can't tell the difference between these two things either. I can, however, distinguish things like this. I can certainly tell the difference between this and this. So the way I'm going to be able to tell the difference between these two distributions is by looking at what happens when I condition on B. This causal graph here on the left is going to produce a different pattern of conditional dependencies than this causal graph here on the right, depending on whether I condition on B. So let me give you an example. If I look at the distribution of A and C in this graph, what you'll see is that there's no causal pathway leading from A to C, and there's no causal pathway leading from C to A, and so I would expect the distribution of A and C together to just simply be the product of their individual distributions. But if I'm going to condition on B, oops, go back here, A and C conditional on B, like this. In this case, I'm going to actually create some dependencies which I can't factorize like so. So I'm going to have to break this f, a, b, and c up according to my previous rule as f of b given a and c times f of a, f of c. Which means, I'm sorry, divided by f of b, which means I'm not going to get this nice product of conditional independence, which I would expect. If these were conditionally independent, I would expect to see something like f of a given b times f of c given b. So that's what I would expect if these were conditionally, a and c were conditionally independent given b. In this case, they're actually not. I can't factorize it appropriately. In this graph, if I condition on B, I use my rules before, so I've got f of a, f of a, b, c divided by f of b. This is going to break up into f of a given b, f of c given b, times f of b divided by f of b. That's going to cancel. And I'm going to get the nice conditional independences that I was expecting. So conditioning on B actually makes these things independent. On the other hand, if I consider them separately, without conditioning on B, I will find that they are dependent. In other words, if I don't condition on B, if I omit this variable, there's going to be a backdoor relationship between A and C that's not foreclosed. It's this so-called spurious correlation that's going to exist between these two, and I won't be able to factorize them like so. So these two graphs are distinguishable from one another, the sort of pointing toward B and pointing away from B. Those are distinguishable from one another because conditioning on the B variable or not conditioning on the B variable creates different patterns of dependency in the observed data. So we can distinguish between those two structures on the basis of observational data. So the idea here is to use the pattern of conditional relationships to identify candidates for the causal network from which those relationships spring. The principle by which this is done is based in a theorem that was originally given by Judea Pearl, who's written multiple articles and books on the topic. He proposes a theorem called the deseparation. I should say his theorems make use of a property called deseparation. So we'll talk about the property and then the theorems upon which that use that property. Deseparation applies to directed acyclic graphs. So the first thing you need to know is what a directed acyclic graph is. It's a graph that's directed and acyclic. So a directed graph is one in which the edges are directional. Which is to say that all of the nodes in the graph are connected to other nodes by edges which indicate the direction of causality. That's not a requirement. We could easily imagine saying A and B are related in some way without specifying which causes which. In fact, there's a whole bunch of ideas and theories that are not theories, but ideas and methods that flow out of that perspective. But we're not going to consider that perspective today. We're going to only consider cases where the graph is directed. Acyclic means that the graph has no loops, which is to say there is no pathway from any node back to the same node. There are lots of things that this acyclicity property rules out. One thing it rules out is something like this. A causes B and B causes A, sort of bidirectional relationship. It rules that out because you can go from A to B in this direction and then from B back to A in that direction. And so you're hosed. The graph is no longer acyclic if you allow those kind of relationships. Another thing it doesn't allow is something like this. I might call this a feedback loop. A causes B, B causes C, C causes A. And the reason you can't do that is because you can go from A to B, and then from B to C, and then from C to A. And these things can be considerably more complicated. These are just two little examples, but neither one of these graphs would be okay, in the sense they would not be acyclic, because you can go from a node back to itself. So an acyclic node has no such loops. There are no nodes for which you can return to itself. So going back to the idea that Pearl's idea of d-separation. So consider two sets of variables, A and B, and a third set of conditioning variables, C. The idea of d-separation is Pearl demonstrates that f of A and B, given the set of conditioning variables C, equals f of A given C, f of B given C, which is just a way of saying A and B are conditionally independent given C for all A in the set A and B in the set B, if for every path between A and B, any A and any B, either one, the arrows on each path meet head to tail or tail to tail at a node in the set C, or 2, the arrows meet head to head at a node not in C and whose descendants are not in C. This is the property of d-separation. So these two conditions here define d-separation. And if C, this is going to sound weird, if C d-separates cap A, the set A, from set B, then we can be sure that that A and B are conditionally independent given C. So this is the property of d-separation, and if d-separation is true, Pearl has a theorem that says that this conditional independence relationship holds. I should note that we used a term here which might be confusing to you, the term descendant. Descendant is just any node connected tail to head from the target. So if you consider this little graph here, A connects to B, D connects to B, and then B connects to C. B and C are descendants of A. So the descendants of A are B and C. The descendants of D are also B and C. The descendants of B are C. C has no descendants. There's also a converse relationship called ancestry or ancestors, which is sort of like a reverse descendancy. Nodes connected head to tail to the target. So for example, the ancestors of C are B, A, and D. Bad. The ancestors of B are A and D. A has no ancestors. So, let's go down a little bit here. What Pearl's idea allows us to do is to reconstruct a directed acyclic graph from a observational data by looking at a pattern of conditional dependencies and independencies, and then drawing the directed acyclic graph that corresponds to those system of dependencies. So Pearl's idea opens the door to ways to systematically construct the network or networks could be more than one, implied by a data set. So let me give you a very coarse example of how this might be done. So what I'd like to do now is to demonstrate how deseparation predicts the pattern of dependencies that might exist among various variables that we see in an observed data set. So what I'm going to do is I'm going to first sketch out a little network here, A, B, C, and D. And I'm going to connect these like so. So A causes C, B causes C, and then C causes D. So what deseparation says is that we should observe a series of relationships among these variables that's predicted by the Pearl's theorem. So for example, if I were to run a regression, let's not do it that way, we'll just say regression, a regression of A against B, we would find no relationship. Why? Well, because Pearl's deseparation theorem says that if we condition, going back to this right here, says that these any two variables will be independent, conditionally independent, if the arrows meet head-to-head at a node not in the conditioning set and whose descendants are not in the conditioning set. So we're not conditioning on anything. There is a node where A and B's pathways, all of them, and only one in this case, meet head-to-head. That's not in the conditioning set. Ergo, A and B are going to be conditionally independent on nothing, on no controls. But if we were to modify this slightly, so that now we included C in the set of conditioning variables, now what we've done is we've broken the deseparation of A and B. And what we're going to find is a connection between A and B. So B is going to be statistically significant, it's going to be related, and C is going to be related. Why is that? Well, go back to the deseparation theorem. A and B are conditionally independent. A and B are conditionally independent if, for every path between A and B, the arrows meet head-to-head at a node not in C and whose descendants are not in C. So for A and B, going here, A and B meet head-to-head at a node inside of C. So that's going to imply that those are going to be related. What about C? Well, we're conditioning on B in this case, going back to the deseparation theorem. In order to be deseparated, the arrows have to meet, the arrows between A and C in this case have to, every path from A to C has to pass head to tail or tail to tail through C. Well, there's nothing in between A and C, so the conditioning variable of B doesn't deseparate the two, so that's why this one's going to be related. What if we were to run a regression of A on D? Well, we'd find that they're related, because we're not conditioning on anything, and in order for A and D to be deseparated, the arrows on each path from A to D have to meet head to tail or tail to tail at a node in C. Well, they meet head to tail at a node, but we're not conditioning on that node, ergo it's going to be related. However, if we were to condition on C, then we would find C related, but D not. Because every path from A to D passes through the conditioning set head to tail. If we were to condition, if we were to model the relationship between all of them, all at once, what would we find? Well, we'd find, okay, so what about B? B meets head-to-head at a node in conditioning set, so B is going to be related. C C goes to A directly. There's no conditioning variables in between, so we're going to find that that's related. D, the path from A to D passes through C in the conditioning set, so D is not going to be related. So as you can see, what we can do is we can predict the pattern of dependencies that exist in this relationship. In a data set, based on the pattern of causal relationships inside of our causal network here, and based on the deseparation property, which tells us that these things are conditionally independent if these two conditions are true. And I should say I believe it's the case that if two variables are not deseparated, they will, as a consequence, be dependent, statistically dependent on one another, related to one another. So the idea of Bayesian networks is to do this process in the inverse, to look at patterns of dependencies and then try to infer what the network is. And that is considerably more complicated than trying to take a series of, a Bayesian net, like this graph we've got right here, and infer the pattern of dependencies which are implied by that network. Nevertheless, it's these relationships that we've just discussed which form the basis for how these networks are constructed. This is not typically how it's done, as far as I know, but one can imagine a giant database, sort of similar to a rainbow table in cryptography, where you have every possible, you have a series of statistical dependencies among a set of finite number of variables, and for each possible set of dependents, conditional and non-conditional dependencies, like the ones we've just established right here, you have a network that are all the possible networks that would imply those sets of dependencies. So in other words, you can imagine running every conceivable regression between all of these variables in this little model here, finding all of the different patterns of relationships given what you put in the model, taking all those results and then going to a giant database and saying, okay, I've done all this in the past. What networks are consistent with this pattern of regression results, and getting an answer. You could proceed that way. It would just take a ton of memory and would be a giant search problem. That's not how it's usually done. But the principle is similar in the sense that we're going to try to look at these patterns of dependencies and then systematically rule out networks that don't fit them. So what I do want to do, rather than trying to go through all of the different algorithms by which we take dependency patterns and reconstruct networks from a theoretical perspective, I do want to show you some software that can go through this process for you, and can, that is to say, can construct networks out of data using the basic principles we've applied. But before I show you that software, first what I want to do is talk a little bit about these patterns of dependencies in Bayes nets and what they mean for regression analysis or some more conventional types of analysis that one might do. So when we're performing a statistical analysis, one of the primary objectives is to block out known or likely cases or causes of spurious correlation. So for example, if we've got a dependent variable and an independent variable like so, and we know that there's something that causes them both, like that, we want to control for that spurious cause so that we can figure out what the path leading from the DV to the IV is. So if we're interested in this, we want to control for the spurious cause. If we don't, if we omit it from a regression, for example, we're going to get a relationship between these two things, which at the very least is stronger than the one that's really there. Actually, I should say not necessarily stronger, it's just different from the one that's really there. For example, I can imagine a case where these things are negatively related. So I should draw this the other way, huh? So the IV causes the DV, and negatively, there's a negative relationship. But there's some spurious cause such that it causes the IV positively and it causes the DV positively. Failing to control for the spurious cause can actually cause this negative relationship to disappear because there's a positive valence pathway through which causality can flow that's opposite of the direct pathway. This is, so-called backdoor pathway. You want to block these backdoor pathways to causality. And causal networks, Bayes nets, I should say, give us a way of trying to assess the kind of things we might need to control for if we are undertaking a regression analysis. So, for example, if I want to control, or if I want to establish the relationship between the dependent variable and the independent variable, and I do a network analysis, and we'll just suppose that it goes through perfectly and recovers a completely correct network mapping, like so. And there's a C variable down here. And there's another variable here. A, B, C. Where am I on? A, B, C, D. I'll call this E. It goes this way. Oh, sorry. It goes this way. And there's a variable here, B. What should we control for? Well, there are actually a couple of different ways to proceed. One is to try to block all of the backdoor pathways from the independent variable to the dependent variable. So, for example, in this case, actually, I'm sorry, I drew this backwards. There we go. So the DV causes D and the IV causes D. IV causes C and then C causes the DV. E causes both the DV and the IV. B causes just the IV. So what should we throw into regression? Should we just throw it all in? Should we just throw some of the things in? Well, I can tell you one thing you definitely wouldn't want to control for. You wouldn't want to control for D. If you put D into the regression, you create a dependency between the DV and the IV that does not exist if D is omitted, and the reason is D separation. D meets head-to-head on the path from dv to the IV, and therefore controlling for D, conditioning on D, deconnects. It fails to deseparate the dv from the IV. What would we want to control for? Well, we might consider controlling, for example, for C, because if we don't control for C, there is a pathway from the IV to the dv that passes through C from tail to head, just like there. And if we condition on C, we deseparate the IV and the dv. E, we've got a tail-to-tail pathway through there, so we'd probably want to condition on E to deseparate the dv and the IV. B is kind of irrelevant. There's no pathway that leads from the IV to the dv through B, so we don't need to control for it. And then one kind of interesting case here is A. Do we want to control for A? Well, it's certainly the case. It is no doubt true that the IV, there's a pathway that leads tail to or head to tail from the IV to the dv through A. The IV causes A, and the IV causes C, or the IV the IV causes A, and A causes the dv. We probably, it's the same thing as here in C, which we said we wanted to control for. But you'll notice that if we control for A, there are no pathways left. All the pathways between IV and dv are blocked. They are completely conditionally independent. They are deseparated. So one point of view might say, okay, well, just like I said for C, we should control for this thing and conclude that the IV and the dv are independent, conditionally independent on these things. Makes sense. That's fine if the goal is to identify anything that goes pathway rather that goes directly from the IV to the dv. If that's the goal, then controlling for A does in fact make sense. But what if we consider both A and C mediating variables, which is to say we want to know the total effect that the IV has on the dv passing through any intermediate variables such as A and C. Well, in that case, we may decide not to control for these things because we want to capture the indirect effect from the IV to A and from A to the dv and from the IV to C and from C to the dv as a part of the process. In other words, if we want to know the total effect passing through all possible pathways from the IV to the dv, we wouldn't want to control for A and C. If we want to only identify direct pathways from IV to dv that don't pass through intermediate nodes, then we would not want, then we would want to control for A and C. Regardless of what we're looking at, we would want to control for E because E is a tail-to-tail node, and not failing to control for E opens up a pathway where the IV does not cause E. In other words, that it's not that changes in the IV prompt or create changes in the dv, rather it's changes in E that create changes in the IV and dv independently. So we would always want to control for E. We would always not want to control for D. A and C is sort of another matter. If we only want direct paths, from the IV to the dv, we should control for A and C. On the other hand, if we want to include all of the possible indirect pathways, that go from the IV to something, maybe multiple somethings, to the DV, then don't control for A and C. So if we can recover a Bayesian network from a pattern of data, it may help us figure out what we need to do in order to estimate what we need to control for, the conditioning set we need to consider when we're estimating the relationship between the IV and the DV. We certainly want to block all of these backdoors like D, and we want to not create a backdoor by controlling for D. We want to block the backdoor between IV and DV through E. But whether to include these intermediate effects depends on exactly what we want to get at, what we want to recover. And that's going to vary according to your substantive application, at least in my opinion. So now let's talk about the software that we use to recover Bayesian networks from observable data. And so what I've done here is to create data according to that matches our earlier example where A and B are independent of everything in the model. C is caused, I should say A and B are not caused by anything in the model. C is caused by A and B, and D is caused by C. So I create a network of relationships according to my network. And I can use the bnlearn library to recover information about those networks. So I'm going to start off by using the GS or grow shrink algorithm. So if you load the bnlearn library, oops, I've already done that, and look at the GS algorithm. GS is one of the constraint-based structure learning algorithms, which uses certain principles developed in publications by Pearl and others to build up a network from a series of independent relationships. I feed it the data set that I've created with all my variables. I tell it I don't want to use parallel computing for this example. The whitelist and blacklist are nodes that we tell it either must exist or must not exist in the network, and we don't have any at the moment. Alpha is 0.05, which tells us basically how big, how statistically significant a relationship has to be in order for it to be called an edge in the network. Let's see. B is, the number of permutations. Yeah, these are just sort of other options. Debug, false. If you set it to debug true, it'll actually tell you each step of what it's going through to construct this network. Undirected, a false indicates that to the algorithm that you want it to recover directionality in the network. So if I tell bnlearn to learn this network based on this data, and then I plot the relationships that exist in the data set, here we go. This is the network that is recovered, and as you can see, it's accurately recovered those relationships. I can, that's just a structure though. It doesn't tell me the size of these relationships, and if I want to recover the size of these relationships, I use the bnfit command, and there are different methods that can use. The default is maximum likelihood. And what I do is I feed it the data set and the fitted network structure that I created. In this case, bn.gs is what I call that fitted network structure. So I tell it to find me or tell me what the strength of these relationships is. And if I look at that object that I've created, you'll see that what it tells you is, okay, well, A is independent of everything, or rather, it's not caused by anything in this network, so it just returns the intercept, which is to say there's no dependence relationships. Same for B. C depends on A and B, and so it runs a regression in effect. Actually, not in effect, it is running a regression between predicting C using A and B. And what we find is that every 1 unit increase in A causes about a half unit increase in C, and a 1 unit increase in B causes about a half unit increase in C. And then D finally is dependent only on C, and so you run a regression between C and D, predicting D using C, and you get a coefficient of -1. And these exactly match the coefficients we came up with in the fake data set. So in short, we can get back things that we put in, which is pretty encouraging. Now, the grow shrink algorithm is not the only algorithm in town. There are others, and they're based on different principles. So, for example, HC calls the hill climbing algorithm, which is a different method based on gradient search, or optimization, I should say, really. And there's the, I think it's MMHC, which is a hybrid of the hill climbing and other, it's a hybrid between hill climbing and other methods that it uses to recover network structure. And we could just as easily use those procedures to recover the structure of a network. So if I use the hill climbing algorithm, I'm going to use the MMHC. There we go. Some of these things are not available, so hill climbing algorithms are intrinsically iterative, so I'm not going to be able to use any cluster information. I can still use a whitelist or a blacklist. Test, I think, is out. Alpha is still in. B is still in. Debug is still in. Optimize is still in. Strict is still in. And undirected is not an option. So if I use the hill climbing, the min-max hill climbing algorithm to recover the structure of this network, I could plot it, and hopefully I'm going to get the exact same thing I got before. This is such a basic network that I would expect to, and I do. Sometimes I'll get different answers, and or sometimes they're subtly different, sometimes they're more different. And that's basically a product of the fact that some algorithms are better at finding structure than others. In this case, the network is so simple that pretty much all these algorithms are going to recover it. I could use, for example, the hill climbing algorithm. And I'm going to get the same answer. In fact, alpha, B, and strict are not options in that one, so I have to eliminate those. But it's something to keep in mind when you have a more complicated network. You might want to try multiple methods of recovering network structure to ensure that your answer is robust to these different approaches. It's also a good idea, if you know for certain that some edges go in a certain direction, it's good to tell the algorithm that so that it can use that information in its fitting process. So for example, suppose that I know that there is a relationship between A and C, and furthermore that it goes from A to C. Well, what I might want to do is create a whitelist that specifies that node. So I might want to tell it, well, there is definitely a node, or I'm sorry, an edge rather, from A to C. Now, that's only one edge. I could give it more. I could say I also know there's a node, or I'm sorry, I keep saying the wrong thing. There's an edge from B to C. Now, if you look at this whitelist, you've got yourself a data frame with from two edges that have to be in the fitted network. So if I use this whitelist in the algorithm, it will turn around and leverage that information to improve the result. Now, as you might expect, if I give it crap in the whitelist, if I give it bad answers, it may or may not react well to that, and you could get very misleading results. So suppose that I tell it there has to be an edge rather from A to B. I've not tried this, so I'm actually not sure what will happen. I would expect it to possibly choke on that information and return a bad network. And it does. If you force it to put an edge between A and B, it may not do a very good job of recovering everything else. it's now saying that C causes B, which we know it's actually the inverse, and it did get C causes D. That's good. But if you give it bad information, you'll get bad answers. If you give it good information, you should get better answers than you get by not putting in that information. And conversely, you can also blacklist things. So if I create a blacklist and I say, look, there's definitely not an edge between B and D. D. Okay, so I've got my blacklist prepared. Now if I rerun this thing again, and now I'm not going to use any whitelist. I'm just going to nullify that out. But I am going to tell it to use this blacklist, that there's no relationship between B and D, which there isn't. I go back to getting the good answer because I've eliminated the bad whitelist. This procedure of using whitelist and blacklist can be pretty helpful in cases where the network is pretty complicated, and adding that kind of ancillary information would be beneficial, would be helpful. Of course, you should only do it if you're certain. So for example, I may know that income doesn't cause gender. It's not the case that making more money turns me into whatever, a man or a woman. But it's very possible that gender causes income through both direct and indirect pathways. And so I might want to specify in a Bayesian network, well, I know there's no edge going from income to gender. It's not the case that money causes gender. But that information is going to allow the Bayesian network to recognize, I can't draw an edge there, and it's going to rule out some of those possibilities that might exist otherwise. The reasoning here is that, as we mentioned before, there are lots of networks that might be consistent with a particular pattern of conditional dependencies. And ruling out as many of those networks as you can with a blacklist or with a whitelist helps narrow down the field to a set of sort of good candidates. So this is, we'll call it alternative fitting procedures. And we'll call this using whitelists and blacklists. Okay. I can also sample directly out of the conditional distribution that's created by a Bayesian network with Gibbs sampling. What I'm doing in this case is just telling it, well, for example, I want to look at all the cases where D is bigger than 1. So D here is at the bottom. And I also want to look at only those cases, I'm sorry, let me phrase that again. I want to look at the probability that D is greater than 1. And I only want to look at that probability in cases where A is bigger than 1. So what I do is I sample tons and tons of realizations of data sets out of this network using Gibbs sampling. And then I look at that pattern of data that I've created, and I say, well, I only want to consider the cases where A is bigger than 1. And then I'm going to look at what's the probability that D is bigger than 1 in that subset of cases. That's what the CP query command does. And what we're learning here is that it's extremely unlikely that D is bigger than 1 if A is bigger than 1. What about if A is bigger than -1? Well, it's considerably more likely. There's 38.4% of the cases where that exists. What I could also do is I could just plot the densities directly. So I could say, well, I want to see the density of D when A is bigger than 1. And what you do is use the cpdist command to generate those densities and then plot them. So this is the density of the D variable when A is bigger than 1. Because you can see it's centered on about, let's say, -0.8. And then if I look at the distribution of D when A is less than or equal to 1, I get a shifted density, shifted up to a mean of about, let's say, 0.2, maybe 0.5, somewhere in that range. So what this is telling me is, as A tends to get bigger, I'm sorry, take that back. As A tends to get smaller, D tends to get bigger. Does that make sense? Well, if you go back to the network plot that we created, I could just create it again right here. Sure, it makes sense. A is positively related to C, but C is negatively related to D. So as A gets bigger, D is going to get smaller, or another way of saying it is, as A gets smaller, D is going to get bigger. All of that relationship is going to pass through C, though. And that's kind of what I was getting at before when I talked about thinking about what you really want to control for when you run regressions. This procedure just tells me as A gets bigger, C gets bigger, and that is a perfectly correct and sensible thing, but we have to recognize that all that relationship is actually flowing through the variable C. It's not a direct edge from A to D. And in fact, if I was to run a regression of D, predicting it using C and A, I would get no statistically significant relationship between A and D because the conditioning set C is there and all pathways from A to D meet head to tail through C. So D separation blocks that pathway. Does that mean that A does not cause D? Well, it kind of depends on how you look at it. It certainly, changes in A will propagate through to changes in D through this network. We can just look at the network and see that. But there's no direct edge. If we wanted to know what's the total effect that A has on D, we could use this simulation procedure that I've just looked at. One way of sort of getting at it as well is just to say, well, I want to not control for C here. In order to see what the relationship between A and D is, with the understanding that C is not a it's not a confounder. C is not a confounder. It's an intermediate variable. And so if I run a regression predicting D using A and omitting the C variable, I could do a summary to get a statistical significance test on that. What we see is, yeah, there is a relationship. As A gets bigger, D gets smaller, which is what we found earlier. Every 1 unit increase in A causes a 0.47 drop in D. Does that make sense? Yes, it does make sense. Is it a spurious correlation? No, it's not. That correlation is flowing through C, which is an intermediate variable, but not a confounding variable. Should we control for C? Well, it depends. Do you want to know how much A causes D through all possible pathways? Or do you want to know how much A causes D directly? So it sort of depends on the question you want to ask. In some cases, you should control for it. In other cases, you shouldn't. I hope what this little exercise demonstrates to you is that throwing in a bunch of variables into a regression as controls is not the best idea. Bayesian networks help us to think about the way that these variables are related to one another, and in turn really help us to narrow down what effects we're trying to estimate and what control variables we need to include in a regression in order to get the effects that we're after. So that's, sort of bringing it back to the beginning, that's one reason why I think that talking about Bayesian networks is a valuable thing to do, because it helps us think more carefully about how we can structure our analyses. You may or may not choose to use Bayesian networks as a tool in and of themselves, but studying Bayesian networks can help you get better at all kinds of analysis, even those not directly related to Bayesian network analysis. Hi, so I want to add a little bit to this lecture. And what I want to add is an emphasis on the limitations of Bayesian networks, and in particular an emphasis on the kinds of networks that Bayesian learning algorithms can and cannot distinguish from data alone. So early in the lecture you saw a demonstration, or a discussion about how to think about whether to include or exclude controls from a traditional regression analysis on the basis of a network mapping. And it's a perfectly reasonable thing to do, but you may not necessarily be able to recover that specificity of information from a Bayesian network analysis alone. Let me give you a little example of what I'm talking about here. So if you recall correctly, we were discussing in that section about control whether you should include things like, for example, I've got a little thing here. If A is caused by B, which is caused by C, you may want to not control for B if you want to include the indirect effect of C on A. And the decision you make there might be different than if, say, B causes both A and C, in which case you probably would want to control for B. That's a perfectly reasonable thing to do, a perfectly reasonable way to think about the problem, but you won't necessarily be able to tell the difference between A causes B causes C from C causes B causes A, or B causes A and C. All three of those things are equivalent observationally in data. And we discussed that a little earlier in the lecture, but I want to sort of emphasize that again in this demonstration of Bayesian network analysis. So in order to do that, I've just prepared three little data sets. One of them, C causes B causes A. So C is drawn from the uniform distribution between -2 and 2. B is just a half C plus randomly distributed, uniformly distributed error term. And A is a half times B plus a randomly distributed error term. If I put all these three things into a data frame and then ask a Bayesian network algorithm, in particular the grow-shrink algorithm, to recover this Bayesian network, it will recover, as you see here, that the three things are related. A and B and C are related. A is related to B, B is related to C. But it doesn't know the direction. It doesn't know, in this case, that C causes B causes A. It just knows that they're related in some way. And in fact, if I do this over again, I'm going to rerun this entire analysis, except now I have A causes B causes C. I get the exact same network. And again, the algorithm is not sure which way the direction goes. Finally, if I have B causes A and C, and so you can see the code is just designed to have B be drawn from the uniform, A is a half B plus a randomly distributed error component, C is a half B plus a randomly distributed error component. If I run the grow-shrink algorithm on this data, again I get the same exact graph. So if I scroll back through, I've got three graphs, all of which look exactly the same, even though the underlying data generating process is very different. Now, I could perhaps identify and separate these graphs if I, for example, added a whitelist edge. That might be able to help me in some scenarios. Or if I blacklisted an edge, that might provide enough information to identify this network more fully. But just on the raw data itself, I can't tell the difference. So when you're thinking about how do I use a Bayesian network to help me structure a regression analysis, well, it may be the case that drawing out a theoretical mapping of how you think these things are related will help you to structure that analysis, but it's not automatically or necessarily the case that a raw data-based Bayesian network fit will help you make those decisions. In this case, for example, all three of these DGPs end up with this same A, B, C in a chain graph, and if I want to know whether I ought to control for B in the relationship between A and C, well, the graph doesn't really help me much other than to tell me that it is an intermediate variable of some kind. While we're on the subject, I also wanted to add a little caution about using Bayesian networks. Remember the assumptions on which they're based and don't try to go outside of those assumptions. One of the assumptions that we had to make in order for Bayesian network algorithms to work is that the graph must be a directed acyclic graph, which, among other things, rules out the possibility of endogeneity. And so what I've done here is I've created an endogenous data set where I'm creating 1,000 observations where the dependent variable and the independent variable are endogenously related. You can see down here, I have to determine the data set observation by observation using matrix algebra problem. In other words, I just solve a matrix equation every time to figure out the solution to these to the endogenous data set, or to the endogenous data generating process. And so what I'm doing is I'm solving for the independent and dependent variables simultaneously using basically let's see, how does this work? So if I recall correctly, this is the BdV is the impact of, this would be of y on x, and BIV is the impact of x on y. So IV, B dot dv is the effect of the dependent variable on the independent variable. B dot IV is the effect of the independent variable on the dependent variable. So if I set this B dot dv to 0, then I basically created a data set without endogeneity. The dv has no impact on the IV. Dependent variable means x, or the dv. IV is the independent variable. I'm sorry, I just said that backwards. B dot dv is like y, or the dependent variable. IV is x, or the independent variable. If I set b dot dv to 0, that means that the dependent variable has no impact on the independent variable, or y has no impact on x, so the data set is not endogenous. But in this case, I've set it to 1, so y, or the dependent variable, does have an impact on x. So if I create a data set with endogeneity between x and y, incidentally, you may have noticed I also put in in, which is just shorthand for an instrumental variable. I've drawn that from the uniform between -5 and 5. The instrumental variable only affects the independent variable, I believe, in this case. Yes, that's right. So this in variable is related to x only, or the IV only. So the correct graph here, if I was drawing a graph, would be IV causes, I'm sorry, take that back. In causes IV, the instrumental variable causes the independent variable. And then the dv and IV both cause each other. So there's one arrow going from IV to dv, one arrow going from dv to IV. That's what I have here. That's the data set I've created. And if I run a two-stage least squares instrumental variable analysis on this data using in as an instrument, I in fact recover the correct relationship between the dv and the IV. So I set the impact of x on y, of the IV on the dv, to be -2. So every 1 unit increase in the IV causes a 2 unit decrease in the dv, ceteris paribus. And in fact, a two-stage least squares regression gets fairly close to that if I use a proper instrument, which I've done here. I've done an instrumental variable. I don't want to get too much into two-stage least squares analysis, just to sort of tell you, yeah, it exists. I can use instrument to correctly solve this problem and correct for endogeneity. However, if I try to employ a Bayesian learning algorithm on the data, I will not fare so well. Let me just spread this out a little bit. So here is what the Bayesian learning algorithm can tell me. It thinks the instrumental variable causes the dv, which it doesn't. It thinks the instrumental variable is related to the IV, which it is, but it doesn't know which direction. And it knows the IV and the dv are related, but it doesn't know which direction either. So if the Bayesian network algorithm were working in a way we wish it would, then it would be able to tell, this instrument only causes the IV and not the dv. And in fact, you would presumably be able to use Bayesian network analysis to identify instruments. You'd be able to say, these in variables are only related to the IV, so we can run a two-stage least squares analysis using them as instruments. But in fact, it cannot do that. It believes, it detects that in is correlated with the dv, which, as you saw in our data generating process, it's actually not. So the warning here is to remember to, first of all, well, just generally speaking, not ask Bayesian networks to recover information that they are incapable of recovering. Don't rely too much on them in situations that are not really designed to be relied upon. That includes trying to distinguish from data alone A to B to C versus C to B to A, or B to A and C. It cannot tell those three things apart. It can distinguish all three of those things from colliders. A causes B, C causes B. It can tell the difference between a collider and all three of those other situations, but it can't distinguish between the three other situations. That's the one rule to remember. Second rule to remember is if there's any endogeneity plausible in a data set, then a Bayesian network learning algorithm probably isn't going to work because, or at least we would be skeptical of it working because you've broken the directed acyclic graph assumption upon which the algorithm relies. All right, so that's it, and I'll see you next time.